Alright, now finally our last representation, which is very similar, and it's sort of a mix between the previous two. So it's called an adjacency list, and essentially it's the same as the adjacency matrix, except for each row is now not in elements. It's just however many elements are connected to the current vertex. So sometimes that's called the out degree of a vertex. So if you notice, vertex 0 is connected to 1, 6, and 8. So I have 1, 6, and 8 here. It tells us to which vertices are we connected. Next I have vertex 1, and that's connected to vertex 0, 4, 6, and 9. So that's what appears in this row. So an adjacency list basically just doesn't include the zeros from the adjacency matrix representation. So we'll start with, again, how do we count the number of vertices, and how long does it take? Well, of course here, the number of vertices is just the number of rows I have here, so that's going to be a constant time operation to return the length of the adjacency list. Next, the number of edges. Well, as you might imagine, we have to loop over each row, and we know in constant time we know the length of each row, because it's just a list, and if we just sum each row. So we're going to say for list and adjacency list, just give me the length, and then I'll take the sum of those. So that's going to be essentially a linear operation. Not essentially, that will be a linear operation, and we'll divide it by 2 if it's an undirected graph, because there will be duplicates. And what do I mean by duplicates? Well, if you notice, 0 is connected to 6, but vertex 6 is also connected to vertex 0. How do we add a vertex? Adding a vertex is as simple as appending an empty list to our adjacency list. So we're just going to add an empty list here at the end. That's a constant time operation. How about adding an edge? Adding an edge is also constant time. So all we need to do is go to our adjacency, I should say AL, not AM. I swear I bug tested this. I'm not sure where the AM came from. So we need to go to our adjacency list at V1, and V1's just plucked out from the input, and we just append V2. So let's say I wanted to add this edge here. I would need to add 2 to this list, and I would want to add a 1 to this list. And I think I'm missing the symmetric list here, or the symmetric edge here. I'm not giving that as an option. So I need to update my code a little bit. Alright, how do you check for the existence of an edge? To check for the existence of an edge, we have to go to the given row and search to see if the corresponding vertex is there. So we'll pluck out V1 and V2 from the edge, and if it's weighted, we'll just check. We'll loop over the adjacency list. So in both cases, we just loop over the adjacency list, and we'll just check to see if V2 is in that list. So is V2 in that list? A little bit simpler code for the unweighted case. Another wrinkle we could put in here is if they are in a sorted order, we could crank this down to log of m. And why is it m? It's because technically all edges could be connected to a single vertex. So in the worst case, we have to look through all edges. So that's going to be either big O of m or a log m if they're in a sorted order, and we can do a binary search again. Alright, how do we find all neighbors of a vertex? And how long does it take? Getting all neighbors is as easy as grabbing out a given row. So if they give us the vertex, we just say, adjacency list, give me that row, and that's a constant time operation. And this turns out to be the operation that we will do most often, is we will loop over all vertices connected to a given vertex. So for example, in pseudocode, when I say for v in and I say graph.vertices at a given vertex, like for example the start vertex in depth first search or breadth first search, this is really what I want. This here would be the neighbors. Anything that's connected to that vertex. Now in code, you might not use find neighbors of AL, a function just like this. This code is just really to give you a flavor for it, to give you an idea of how this works. But in your own implementations, you don't have to have everything coded up exactly like this. All right, and finally, let's look at how much time, how much memory, sorry, is used to store an adjacency list. Well, for each vertex, we have to have a list. Even if it's an empty list, that's going to take up space, so that's going to be the n in big O of n. And then we also have to have space for each edge. So if we added up all these rows, that's going to give us m edges. So it's big O of n plus big O of m. So we can count the number of edges, and we can do our same little finagling here to figure out if we're storing things as floating point numbers or bytes. We can see if it's weighted, and we can calculate our total memory usage.